Okay, welcome back. Today, we're going to talk about Chapter 7 and the central limit theorem. So, what the central limit theorem deals with is it deals with taking samples for something that we know a little bit about and figuring out what the distribution of those samples would be. Let's take a look at the theorem here. We're going to let x be some random variable. We will know what type of distribution x has. We might not even know what it does, but we do know the mean and the standard deviation of x. X might be something that's normally distributed, uniformly distributed. We've talked about a binomial distribution, or it could be something that we haven't discussed, but it's something where we were able to measure the mean and the standard deviation. And then what we're going to do is we're going to repeatedly take samples of x of size n. So x represents the idea of I've got my population. I'm going to take one member of the population and see what I get. That's x. With the central limit theorem, we're looking at x with a little bar over it, which says instead of just looking at one member of the population at once, let's look at n of them all at once. And I can repeat doing that. So I can repeatedly take samples of size n. And each time I take a sample of size n, I will calculate a mean of that sample. X with a bar over it represents my ability to keep taking this and recording these means. So x with a bar over it represents the distribution of the means that I get when I repeatedly take these samples. What the central limit theorem states is that if n is large enough, in this class we're going to say at least an n of 30, then x bar will have a normal shape. No matter what shape the original x had, we don't care. X bar is going to have a normal shape. The mean is going to be the same as the original mean. For the standard deviation, we'll need to take the original standard deviation and divide by the square root of the sample size. Or in other words, the more things we sample, the less varied those means will be, which makes sense. If you sample a larger number of things, then the odds that your mean of your sample gets closer to the actual mean of the whole population becomes more likely. Whereas if you only sample a couple of things, then it's more likely that you could be very far away. When you sample at least 30, we're going to say that that distribution is going to look normal. Now, there's a lot going on here in this theorem, so let's go ahead and do a visualization of all of the different moving parts and put them together. So, we've got some entire population. And for this population, you can take individual members of that population and calculate their statistic. So let's go ahead, for example, and say that I've got all of these different things. All of these different things, an individual from there. If we measure something, we might say that I'm going to measure that thing, I'm going to call it little x. Capital X represents all of the different measurements together. And capital X has a certain mean, which we'll call mu x, and a standard deviation, which we'll call sigma x. So I can measure for all of these things. It would be the whole population. It would be usually unreasonable for us to do it if it was big enough. We can find the mean of the whole thing. We can find the standard deviation of the whole thing. The central limit theorem deals with taking samples. So I'm going to take a whole bunch of different samples. Ideally, they're random samples. So I'd take a random sample. In this case, for each of these, n equals 5. And we do want the sample size to be the same with each one. For each of these individual samples, we would calculate the mean of the sample, which we would call x with a bar over it. Each of these individual samples has a sample mean. If we group all of these means together, we can treat that as its own variable, which we can also calculate a mean and a standard deviation. The mean will be the same as the original. The standard deviation will not. It will be the standard deviation of the original, standard deviation here, divided by the square root of the sample size. The final piece of the central limit theorem says that if n is large is a subjective term. In this class, we're going to say at least 30, then x with a bar over it is normal. The larger n gets, the closer x bar gets to normal. We're going to say in this class that as long as it's at least 30, it's close enough to normal that we can do math on it as if it was normal. If it's smaller than 30, it's not quite close enough. If it's larger, then it is even more precisely normal. But 30 is big enough that we can do the job. In this case, we only had 5 elements in each sample, 5 members of the population. And so this example, it actually wouldn't be close enough to normal that we can approach it as if it was normal. But if I had 30 little bubbles in each sample, then we could go ahead and treat x bar as normal. I don't care how many different samples we take, because usually we're not actually going to take a whole bunch of different samples. We're just going to imagine the idea of what would happen if we did and use that to analyze the results from just one sample. Let's go ahead and do 2 examples following this idea. The first one, we're going to talk about SATs. This time, instead of looking at the scores on the SATs, we're going to look at the distribution for how long it takes. It tells us that for a group of students, it will normally take 2.5 hours, and there will be a standard deviation of a quarter of an hour, 15 minutes. And it's asking us first, we want the probability that a randomly selected student takes longer than 2.7 hours to finish the exam. Now we know how to set this one up. If we were to go ahead and sketch a graph, we would have a 2.5 here. The standard deviation would be 0.25 going in both directions. We are looking for, at 2.7, right around here, the odds that it is in this area. Now, we would approach this using norm dist, since we're going to go from a number to a percentile. 2.7, 2.5, 0.25, and of course, always true. that will represent this part of the graph. Because remember, norm dist always measures to the left of a certain value. I'll plug this into Google Sheets on the side real fast. And it gives us 0.788 for this part. Which means that the part we're actually looking for is going to be 1 minus 0.788, which is going to be 0.212. Now, for part 2, it's asking us something very similar. The probability that the mean is longer than 2.7 hours. But we're not looking at an individual anymore. We're looking at a sample of 36 individuals. So we're saying we take out of all of the students who took the SATs, we're taking 36 randomly, and we're finding the mean of what their time was. Some were probably a little longer than average, some were probably a little shorter than average. What's the odds that this mean of what we took is going to be larger than 2.7? Now, we'll be approaching this in a very similar way. The mean of our sample is going to be the same as the original mean. The standard deviation of our sample is going to be the original standard deviation divided by the square root of the n, which is 36. So that will end up giving us 2.7 divided by 6, which comes out to be 0.45, a much smaller standard deviation, which makes sense. A single student is fairly likely to be somewhat above or below average. But if I were to sample 36 students, it would be very unlikely that all 36 of them were above average or below average if I did my random sample correctly. So therefore, with this graph, it ends up being a much skinnier graph than the last one. The mean is still at 2.5, but my standard deviations are much smaller, 0.45, compared to my original graph. When we plug in the norm dist into Google Sheets, same 2.5, same 2.7, same 2.5. We'll use the new standard deviation that we calculated of 0.45, and of course, always true. This time, we got out a different number. We got out a 0.67. Actually, sorry, we need to fix this because we've used the wrong standard deviation. 2.7 wasn't our standard deviation. That was the value we're comparing. We're supposed to plug in the 0.25 here and divide that by 6, which will give us a very different answer. So we'll take the 2.5 and divide that by 6. 0.25, excuse me. And that gives us a standard deviation of 0.0417. We'll plug that into the norm dist. So we're plugging in, let's change the color to match. It's the same 2.7 to find this shaded area. Norm dist of 2.7, 2.5, 0.0417, and of course true. That gives us out 0.9999991. And suddenly, we see that the odds of the other region, the part that we're actually looking for, are incredibly small. 0.000009. Why did this happen? Well, once again, if I'm just looking at one student, I say, what are the odds that this student was a little above average? That seems like a reasonable thing that can happen. One student might be a little faster on the exam or a little slower. But if I'm taking 36 students all together, and I'm looking for the odds that all 36 of the students are moving above average, that is wildly unlikely. If we repeat the experiment with 100, well, we can go ahead and see what it will be. The standard deviation will be 0.025 here, because it will be the 0.25 divided by square root 100. So that gives us 0.025. And when we plug that in and subtract from 1, Google Sheets says it's basically 0. It can't even tell how small that odds are. It's not even worth considering. It's insanely unlikely that if we sample 100 students, their average would ever end up being larger than 2.7. Now, obviously, depending on the scenario of what you're looking at, whether something is likely or unlikely to happen is extremely relative. What we're going to say, if we don't specify, is that something is unlikely to happen if it is more than 2 standard deviations away from the mean. We will give more specific examples of things like this when we get to chapter 8. For now, 2 standard deviations away is enough that we'll say that's too far away. That shouldn't have happened. That's unlikely. For example, if we sampled our 36 students and we found that on average they took 3 hours, not 2.7, then we would think, well, okay, either I had the 1 in 10 million chance that my students happened to be that much slower at taking the exam than the average, or more likely, something about my sample is not following this mean and standard deviation that we believed. Maybe, for example, the room of students that I walked into was actually a group of students who were much younger and trying the SATs ahead of time. And so these 36 students were expected to take a little bit longer. Or maybe the original information that I was given is just simply not true. And that information is actually false. And so it looks like my thing was unlikely to happen, but in fact, it was expected to happen. Just my information wasn't good. That's what we're trying to look at when we're doing these tests. If I found my sample and it gave me a certain mean, do I think this sample is following the same rules that I was given? And if not, why do I think that might be? Let's go ahead here and go through some examples. Coke and Pepsi are both claiming that every soda can is filled with 16 ounces of soda. And we know that the standard deviation is 0.15 ounces when you are dealing with soda. We're going to test 50 cans from every single company. For Coke, we find a mean of 16.02, and for Pepsi, a mean of 15.95. Let's just go ahead and graph what this is before we even look at what the problem is asking us for. Okay. I'm first going to graph original x. This is the original graph for what we think the distribution of soda is. It has a mean of 16 and a standard deviation of 0.15. Then we took a sample of size 50. That gives us the graph of x bar. Remember, x bar is going to be a much skinnier graph because we're expecting the standard deviation to be much smaller. By repeating the process of taking a sample, the more people that we sample, the less variable we'll get. And so we expect the mean to be the same 16, but to have a much smaller standard deviation. We can calculate what we expect that standard deviation to be. It's the original standard deviation divided by the square root of n. In this case, that's 0.15 divided by square root of 50. The square root of 50 we know is about 7 because 50 is one more than 49. But we can go ahead and calculate exactly what that needs to be. The number we get is 0.0212. A standard deviation that is almost a tenth what the original one was. Using all of this, we can now try to look at what's going on. Coke's right here, and Pepsi is over here at what we calculated for their sample. We need to know, is this company's claim that they're actually putting 16 ounces in every can, given the standard deviation that we know? Is that claim actually accurate? Or do we think that the companies are maybe not giving us all the whole information? Or maybe our sample was wrong? Basically, does our data line up? That's the question that we're asking. Now, there's a couple ways that we could go about doing this. The first way, the easier way more likely, is to find the z-score. Because we just need to see if the z-score is between -2 and 2. So let's go ahead here. The z-score for Coke will end up being 16.02 minus 16 divided by, we'll always use this standard deviation because we're looking at the full sample. So 0.0212. And we'll see what that comes out to be. I'm getting a z-score of about 0.943. That is smaller than 1 standard deviation, much smaller than 2 standard deviations. So we say this is within variation. It's not extremely normal. This sample is certainly above average, but it's not so far above average that we expect that Coke was lying about their numbers. Whereas, let's do the same thing with Pepsi. So that will be 15.95 minus 16 divided by 0.0212. Plugging this into our calculator, we obtain negative 2.358. This is less than -2. So we will say it is not within variation. What does this mean? Well, it could mean a couple of different things. Maybe the original claim that 16 ounces was the mean was incorrect. Maybe Pepsi's undercutting us. They're not filling each can up the full way to 16. They're only filling it up to 15.95 or something a little bit less. And so they're trying to save a little bit by underfilling each bottle. Quality assurance programs will do this all the time to make sure that soda companies aren't lying about how much they put in. They're always telling the truth, and we can take these samples to make sure. Maybe that standard deviation, the 0.15 ounces, was wrong. We don't actually really even know where that standard deviation came from. So maybe that standard deviation wasn't quite correct. We'd have to do a little bit more research to figure something out there. And that type of research is not something we'll cover in this class. Or maybe we did just get a very unlucky sample. Maybe we happened to take a bunch of cans that were just underfilled relative to the rest. At which point, when we get this result, typically the first thing you would do is you would repeat the study and see if you get a similar result. Because the more repetitions we do, the more likely it is that we find out the truth. If we repeat the study, say, a dozen times, and every single time we find out that it is much below average, then that tells us, yeah, these Pepsi cans are actually being underfilled. We should go ahead and we should audit the company. That's all we've got for today. See you guys next time.